So today we're going to start chapter 6. Chapter 6 is on alkyl halides, which we know something about, and their characteristic reactivity. So we've defined alkyl halides. It's basically what you get when you take a hydrocarbon and replace one or more hydrogens with a halogen, halogen being fluorine, chlorine, bromine, iodine. You'll notice there is technically a halogen below iodine, astatine, but that stuff doesn't have any long-lived stable isotopes. So it basically, it's not an element that you can use, that you can easily incorporate into an organic molecule. But I'll have to get chapter 6 up, and it will not be due any earlier than Friday, but I intend to be fair. Let me just get home and look at the assignments, and if I intend for it to be due on Friday, I'll make sure that it goes up today. Doesn't make much sense to, yeah, Merry Christmas. Yeah, you will not really be doing still homework on Christmas Eve. Don't worry about that. It will be due either this Friday or the following Friday. Good. So, right, so I didn't want to put it up anyway before we actually started the class material. So now we're actually going to start chapter 6. So I would say that in general, alkyl halides are able to undergo two broad classes of reactions. We're going to talk mostly only about one of them, and that is nucleophilic substitution. So we've already defined nucleophile. Nucleophiles are Lewis bases, and I think I've already pointed this out, but nucleophiles are Lewis bases, electrophiles are Lewis acids, and honestly, I'm being as honest as I can with you guys, I see no significant difference between those two sets of terms. I do not know why there are two sets of terms. It might be that some are better used by experts in like academic journal articles in one situation as opposed to another, but in terms of even everyday use for sort of an organic chemistry professor type like me, I don't see any meaningful difference between those two sets of terms. So one thing that we know, or one thing that we're going to cover in this chapter, and probably the main thing we're going to talk about, is that if you have an alkyl halide of this type, so X is a halogen, fluorine, chlorine, bromine, iodine, and X can be other things too. We might run into a couple of those, but I think for our purposes, X is mainly going to be a halogen. And of fluorine, chlorine, bromine, iodine, probably more so bromine and iodine than either chlorine or fluorine, though alkyl chlorides will react. Alkyl fluorides can, but they're a little bit more difficult because the carbon-fluorine bond is pretty strong. So I think you'll find that in general, the larger the halogen, the better in terms of this type of reactivity. And these groups X that are attached here, we call them the leaving group. And I'm just defining some terms here. So we call it the leaving group because that's exactly what it does. It leaves and is replaced by some Lewis base or nucleophile. You're going to see something having this lone pair of electrons here. Something has an extra pair of electrons to donate, to act as a Lewis base, and it will replace the leaving group. And instead, you'll get the leaving group as part of an inorganic side product. This might be a neutral molecule, or it might be an anion. So I'm not being specific about charges here. However, in any case, the charges will add up right. Oh, let me talk about REEF today. Everyone, please register their attendance, but I do have a couple of REEF questions later. So, so please do be sure you stay for those. They are going to be on chapter 15, which was not in your exam, but I haven't asked you about it yet. So there will be a REEF session later. Let me at least get through some of the material first, and then we can worry about the REEF session later. So where were we? So this is I guess, a schematic you can, as you might say, of a nucleophilic substitution reaction. And this falls under the umbrella of substitution reactions in general. And we define substitution reactions earlier in this term as being those in which two groups or two separate species switch places. And I think you can see that's exactly what happens here. The leaving group and the nucleophile switch places. And that's always going to be the case with a nucleophilic substitution reaction, no exceptions. And I should also mention, talking about nucleophilic substitution reactions is a little bit different than, say, talking about halogenation of an alkene or acylation of an aromatic compound. in that it's much more broadly and generally considered than those other classes of reactions that we discussed earlier. So there's more than just one class of reactions, but there's many types of reactions that one can conceive of, and we'll go over a number of examples, of course, that fall into the category of nucleophilic substitution reactions. Now, there is another class of reactions that alkyl halides undergo in general, and these are called elimination reactions. And we've defined eliminations earlier. We said an elimination reaction is one in which one molecule breaks up into two or more molecules. For that reason, they're sometimes also called decomposition reactions, but I think they're usually called eliminations. And in a typical elimination reaction, we have a little bit more going on than just our leaving group, but there's going to be a carbon next door to the carbon bearing the leaving group that has at least one hydrogen directly attached. And then, instead of a nucleophile broadly, we're going to treat this with some kind of base. I'm just going to write B with a lone pair here like this. So this is going to be some kind of Bronsted-Lowry base. And some bases you can recognize, I think, and any kind of hydroxide, sodium hydroxide, potassium hydroxide, those would fall under this category. These are usually anionic. There are neutral bases, to be sure, but they're often anionic. And in the end, you're going to get an alkene out of it. You're going to eliminate eliminate the equivalent of HX, and your organic product will be an alkene. And there will be other inorganic products besides. You'll get, I suppose, the conjugate acid of that base, whatever it is, BH we can call it. And you'll also get whatever that leaving group ion is. Probably it will be an anion. Usually leaving groups are neutral when attached to the carbon and anionic after they've been liberated. So this is another thing that alkyl halides can do, again, as long as there's at least one hydrogen next door. So I'm going to try to be as blunt as I can. I've noticed I do better down south with my usual East Coast bluntness. They tended to be offended in the Midwest, and I had to be more, indirect, but I can just say stuff here. I really like that. And likewise, also, I like how down here, if there's a problem, people tell me. I can't just read your mind, nor do I expect you to read mine. Anyways, what I expect you to get from what we've had so far, and I don't say this is an exhaustive description, but what I expect you to get out of this is that things with halogens attached, is that general enough for alkyl halides? Things with halogens attached to carbons, make sense? Can undergo two types of reactions. The main one we're going to talk about is called nucleophilic substitution. And we already know what a substitution reaction is. It's this group and this group switch places. And so you get a substituted product looking something like this, plus an inorganic side product that's going to involve your leaving group. Or it is also true that alkyl halides, provided there's at least one hydrogen directly attached to an adjacent carbon to the one that bears the leaving group, and when treated with a reasonably strong base, will lose the H and the leaving group and form an alkene. And in the end, you will get some inorganic side products as well. Mainly, we're going to focus on the major organic product, which will be an alkene. And it's good for you guys to be aware that reactions like this also occur, but we're going to mainly talk about nucleophilic substitution. Now, just to give you sort of a general overview of this, the truth is that there's two different types of nucleophilic substitution reactions called the SN1 and SN2 schemes, and those we're going to talk about in some detail. I'm not going to go as deep as I might, but in some detail. There's also two types of elimination reactions that correspond pretty well to SN1 and SN2. They're called, unsurprisingly, E1 and E2. And actually, there's even a third type of elimination reaction called the E1CD reaction. And all that together makes for an admittedly rather complicated but in some ways, very attractive picture, how all of that works together. But I just don't see, again, the need for us to go that much into detail about the elimination reactions. I would like you to know that it's possible to make alkenes from an elimination reaction, especially starting with an alkyl halide, and reactions equivalent to that do happen in living systems. Generally, we find very, very few halogens involved in living systems. Normally, our leaving group in a living system is some kind of phosphate ion, which we've already introduced. And all that is fine, but I'm going to focus on the SN1 and SN2 reactions. Those two kind of make a little system of their own. And without worrying about overcomplicating it with the elimination stuff, that's mainly what I'm going to focus on. Now, as usual, I've left some questions on elimination reactions in the Chapter 6 OWL assignment, which again, if I mean for you guys to finish that by Friday, I will make sure to get that up today, probably right after when I get home from work. And I've left them in there so that you at least get some exposure to those ideas, but we're going to focus on the nucleophilic substitutions. And so I think that's a good place to start. So what might an example of a nucleophilic substitution look like? Let's just look at one example. Maybe if we took the ethoxide ion. This is CH3CH2O-, and that's a species you can get your hands on. You can take alcohol, and rather ethanol, and treat it with a really strong base, and it will pull, sorry, minus charge, it will pull the proton off the alcohol. But this is a species that you can get. And let's say that we treated it with, oh, let's use colors. Yes, sorry, I always get excited. Oh, that's a pretty bad color choice. Let's use red. Let's say that we treated this with benzyl bromide. So pH for benzene ring, C6H5. So this is a benzene ring with CH2Br on it. That's a very typical electrophile. And these two compounds I would expect to react quite readily. And what you would get is the ethoxy group taking the place of the leaving group, of the bromine. The leaving group won't always be bromine. I just don't want you to memorize that Br goes there. Could also be a chloride or an iodide. But in any case, what I'd expect that we would get out of this, well, we can do it that way too, is the product that you would get if you remove the leaving group and put this nucleophile in its place. And I think you will agree with me, that would look like this. Of course, the oxygen no longer is a minus charge. The electrons, the extra electrons in the minus charge were used to make a bond here to that carbon. And yes, you will also get the bromide ion. You'll know what you have to write based on how the question's phrased. Sometimes OWL wants you to write those anions, but we're mostly interested in the major organic product here. And actually, to the extent that we talk about ethers later on, we'll learn that this is one of the best ways there is to make ethers. This is known as the Williamson ether synthesis, and it's nothing other than an SN2 reaction. So what you need to know is that you should look at the nucleophile that you're given. You should be able to identify something with extra electron pairs on it. And then look also at the other species, the substrate, the one that bears the leaving group. And by the way, substrate here is used very much in the same way that biologists use it. They'll talk about the substrate of an enzyme, meaning the thing that the enzyme acts upon. So same thing, the substrate here is the molecule that the reaction acts upon, the one that contains the leaving group. So the substrate always includes the leaving group. Always. The substrate always includes the leaving group. No exceptions. So anyway, if you look at your substrate, you'll see a leaving group, which again, probably for us will be a halogen. And you look at your nucleophile and you replace the leaving group with that nucleophile. Do you see how I've done that there? I've just swapped them out. Everyone say, I've tried to color code everything. So can everyone see this ethoxy group comes from the ethoxide ion? And all I've done is I've replaced the leaving group with this nucleophile, and that's going to be my major product. So that's how you know what the product is going to be. You just do a substitution reaction. You switch the leaving group and the nucleophile. You should get in nearly all cases anyway, a neutral organic molecule. We'll do other examples, but I just want to make sure, does that make sense? Everyone following so far? Oh, and I should also mention, usually, well, not usually, you can't have a bottle of minus charges or a bottle of plus charges. So there has to be something associated with this anion. Most likely, it'll be an alkali metal ion, Na plus, K plus, something like that. You'll notice we don't even need to mention that. Those species are, well, okay, we don't have to mention that except when Al wants us to, which sometimes they might, so read the directions carefully. But there's not going to be a bond between an oxygen and everyone talking to me in chat. There's not going to be a bond between an oxygen and an Na plus or a K plus. That's an ionic bond. It's not covalent. And so any other cation here, the metal cation, doesn't play any role in the chemistry. It's what we call a spectator ion. One of the few terms from Gen Chem that is of the type that I love so much because it means exactly what it sounds like. The spectator ion is something that doesn't do anything in the chemistry, but just floats around and watches. And so that's what that does. And ultimately, you will get some kind of inorganic salt here, like NaBr or KBr or Ki or something like that. But the major organic product will be the result of nucleophilic substitution. And if we can get that down, I think we're in pretty good shape. Let's see. Which does beg the question, could one take not O minus, but ethanol itself and treat that with benzyl bromide and still have some hope of getting the same molecule? And the answer is yes, that would work to some extent, except instead of Br minus, you would get HBr in the end. But what we find is that anionic nucleophiles, and I'll write this down in a second, anionic nucleophiles, which means nucleophiles with a minus charge, other things being equal, react more quickly. They work better than neutral nucleophiles. So anionic nucleophiles react faster than neutral nucleophiles. And again, this is going on YouTube, hi YouTube, so you can stop here and listen to me say that 17 times. Pause the video right here so you can copy that down, so you don't need to worry about a thing. That's all going to be available. And as I said earlier, I'm of two minds in terms of the mouse writing here. At this point, I'm kind of used to it, but I don't so much mind putting out the money to buy a stylus. I just then think, what if this computer, being as locked down as it is, doesn't even recognize the stylus? I should look, because I do think I have one of those artist's tablets at home somewhere. So I'll take a look. If I have one, we'll try it one day. I do question whether this would turn out to be any neater because the screen is so small. But we can give it a try once. We'll see how it goes. So, and that kind of makes sense because the neutral nucleophile is at first going to give something like this that still has the hydrogen attached and will have the plus charge. And now you'll need something to come in and take off that proton to give you the neutral product. So it's a less efficient reaction. So other things being equal, let me write over here also OTBE for other things being equal. But other things being equal, anionic nucleophiles react faster than neutral nucleophiles. So I would expect the anionic nucleophile to give a faster reaction than the neutral one. This would still be an example of a nucleophilic substitution reaction, but I think you'll find the one with the anionic nucleophile will be much more efficient. let's see. Let's just give maybe another example. Good. Let's say that we reacted sodium hydrosulfide, NaSH. Since you might be given it as a metal salt also, it might not just give you just the anion. And let's treat that, I already used benzyl bromide. Let's use 1-iodobutane. Let's say we reacted these two species. What would we expect to get in terms of the major organic product? Well, what you need to know is that when you see an alkali metal salt like this, what you're really saying that we have is the anion, in this case, the hydrosulfide anion, which looks like that. Na plus is just a counter ion. That's a spectator ion. That's not going to play any role in the reaction. And again, I feel your pain. I have taught Gen Chem. I understand this. One thing I've probably said 10,000 times is ionic compounds would be so much easier for students if they were written like this. That would make everything so much easier for students. Instead, what I wound up saying 10,000 times is the charges are still there, we just don't write them. So you need to know that. You need to be able to recognize ionic compounds. They're going to include a metal and a non-metal like that. So you covered that in Gen Chem. So whenever you see something like that, please understand the charges are still there, we just don't write them. Why, I don't know. That decision must have been made between 100 and 200 years ago. And none of us was around to complain at the time. So that's important that you understand what's going on when you're looking at an ionic compound. And I would say, even if it's an ionic compound you've never seen before, probably this is such a compound. Anyway, once we understand that this is our anion, this is our nucleophile, and the way I know it's a nucleophile is because it has extra electron density around it. And these alkali metal salts often are. And so this over here is going to be our substrate. That's going to be the molecule principally acted upon, with iodide being our leaving group in this case. So again, remember our rules. You look at your substrate and find the carbon that the leaving group is attached to. Then you look at your nucleophile and you put it in place of the leaving group. And that's going to be the organic product. So I would expect to get this compound. In this case, it's a thiol. You can call that butane thiol if you want to, or not. I promise my feelings won't be hurt. And yes, you will in addition get, I guess, sodium iodide, right? If it were to ask you what the inorganic side product is, you would say sodium iodide is an inorganic side product. Normally we don't mention those just because we're so much more interested in the major organic product than we are in these inorganic side products. But if you did want to balance the equation for mass, then that would be there also. Good, so there's another example of a nucleophilic substitution. So if you're following so far, what you get is that if you need to figure out the product of a nucleophilic substitution reaction, first identify what your substrate and the nucleophile are. And again, you could be given either of these types of things for the nucleophile. You might be given it as a salt, you might be given it as an anion, or the nucleophile can also be a neutral molecule. We did that a moment ago with ethanol instead of F-oxide ion. So you need to be ready for any of those possibilities. But once you've identified those two species, you simply replace the leaving group with the nucleophile, making sure that in any case you wind up with a neutral molecule as the product. You always want to get a neutral molecule for your organic product, at least almost always. And then anything else is going to be some kind of inorganic side product. I don't really care if you can name thiols, but I would call that one butane thiol. At least you guys know what thiols are, I hope. So that name's not real surprising. Good, so that's just another example of a nucleophilic substitution. Where are we at? Oh, we're doing pretty good in terms of time. So I would really love to begin to get into the SN2 reaction. I'd like to cover that one first, since it's, to my mind, simpler. And then maybe for the last, 7 to 10 minutes, we'll do our reef session. Certainly do make sure you register your attendance, please. I want to make sure that we do that, because that's going to be 8 out of the 10 points, is just attendance. Good. Any other questions on nucleophilic substitution in general? I'm going to write here the SN2 reaction. Is it okay if by now I do RXN for reaction? This stands for substitution nucleophilic and the 2 stands for bimolecular. Bimolecular. Good. So bimolecular can be defined a couple of different ways, I would say. One of the things that bimolecular means, and we'll show all this as we get to examples. One of the things that bimolecular, let me back up a little bit. What does bimolecular mean? Well, it means that there are 2 species involved in the rate determining step of the reaction. There are 2 molecules, 2 things involved in the rate determining step. What that means is when we write out our rate law, it's going to be second order. So second order kinetics. But you can look at it either of those 2 ways. It's just 2 different ways of saying the same thing. And so what I'm going to do now is to go over, at least to some degree, the characteristics of a typical SN2 reaction, and I will do so until, at least for a few more minutes, and then we'll, I'm expecting we'll continue that next time. But let's see. But I basically want to make sure that we end with how you're going to know whether we're looking at an SN2 reaction or next time an SN1 reaction, which, as you will already guess, stands for substitution nucleophilic unimolecular. For that one, only 1 molecule is going to be involved in the rate determining step. So let's see. A typical SN2 reaction might look something like this. I'll take methyl iodide, and we'll add the cyanide ion. So in Gen Chem, you might have written this as Cn minus. And that's certainly not wrong, but wait a minute. But, you know, be aware for sure that the minus charge is in the carbon, not on the nitrogen. So this is actually a kind of carbanion. Anyway, if you did this reaction, you would get CH3CN, since, as we've said, the nucleophile replaces the leaving group. And that's going to be your major organic product. There's still a triple bond here, of course, and there's still a lone pair on nitrogen. And the other bit that you will get will be the iodide ion that comes from the methyl iodide. And I would expect something very similar to happen if we used methyl bromide or methyl chloride. In real life, we really love to use methyl iodide if we're going to use something like that, because methyl chloride and methyl bromide are gases at room temperature. It's a huge pain to deal with that. Methyl iodide's a liquid, and so it's easier to measure it out and add it to something. So this would be a typical SN2 reaction. What we would find about such a reaction is that if we were to write the rate law, it would be second order. So again, I'm assuming you at least brushed on rate laws in your Gen Chem class, meaning that there's going to be 2 terms besides the rate constant. It's going to be the rate constant times methyl iodide concentration times cyanide ion concentration. I'm just going to write Cn minus here just for simplicity. So both of those species are involved in the rate determining step. That's why they both show up in the rate law. And so we would call that a second order, or we would say this reaction has second order kinetics because there's two terms, both of course to the first power. So 1 + 1 is 2. This is a second order reaction or second order kinetics. And yeah, I know, you got very mathy with this probably in Gen Chem. We could still do that if we wanted to. We could plug in numbers for the concentrations and figure out what the rate is or solve for the rate constant. We could do all sorts of stuff until we're blue in the face. I don't want to do any of that stuff here either. I don't think that's appropriate for an organic chemistry class. But all this is, two molecules are involved in the rate determining step. How does it work? Well, I'm going to show that next. We're going to go over the mechanism, which is very simple. And again, I've said this before, I'm not going to focus very heavily on mechanisms, but for these two types of reactions, they're pretty simple, so I see no reason not to. The way the reaction would work in terms of its mechanism, let's write our methyl iodide over here. I'm treating that carbon as though it's chiral. It is not. But here's our methyl iodide, and here comes our cyanide ion. That's going to come in from the opposite side of the leaving group. And remember what we use arrows for. It's always and only to show the movement of electrons, never atoms, never charges. So what happens is this cyanide ion comes in from behind the leaving group. I might have told you organic chemistry is a violent science. We would say the cyanide ion attacks this substrate from behind the leaving group. And yeah, those 3 lone pairs are still there. And in so doing, it breaks the carbon-iodine bond. We'd better do that because otherwise carbon would have 5 bonds. And we'll put the electrons in the bond onto the iodine atom, and that will make an iodide ion. And there's actually a transition state in which this molecule will actually invert like an umbrella in the wind. Maybe we'll say more about that the next time. But in the end, you will get, actually let me put it over here. Well, you'll get this compound. And of course, those 2 other hydrogens are still there. Let me not forget my lone pair on nitrogen. So still a tetrahedral molecule, and you will of course get the iodide ion also. Electron goes back an iodine atom because it is more electronegative, right? Exactly right. Couldn't have said it better myself. Or at least it's electronegative enough that we can believe easily that it could bear the minus charge. That looks horrible. But indeed, that's true. Halogens are more than electronegative enough, all of them, to be able to bear a minus charge like that. But the major organic product will be this one. So, and I'll end with this, what does this have to do with, at least before we go to our reef thing, what does this have to do with the rate determining step? Well, this reaction has only one step. That's it. It happens all at once. The nucleophile comes in, kicks out the leaving group, and you get your product all at once. And we said that the second order rate law means that both of those molecules are involved in the rate determining step. And indeed they are. Here's your cyanide ion, here's your iodide. So I will just say more generally what you need to know is for any SN2 reaction, the rate law is going to be rate constant times substrate concentration times nucleophile concentration. That will in general be true for any SN2 reaction, no exceptions. Can I just go NU with 2 dots like that for nucleophile? Is that okay? Just to save us some time. And you'll see that's exactly what we've done here. The methyl iodide is our substrate. We know that because it has the leaving group. The other species is the nucleophile. It has a minus charge. Most nucleophiles do, not all, but most. So Anytime we have an SN2 reaction, the rate law will always be of this type. There are no exceptions. And I would say the opposite's also true. If you come across a nucleophilic substitution reaction in the wild, and it has a second order rate law, you can be sure it's SN2. There will never be any exceptions. So this is some complicated stuff, and I'm going to kind of start here on Wednesday. But I want to make sure that we get through our reef session, at least I'd like to. So let me see here. Let's move over to that. I want to make sure that everyone can see. And once again, I've taken away the answers, so you don't need to worry about that. So let me see. I have two questions today. First one is concerning lipids. This is something we talked about from chapter 15. Seems like forever long ago. Which of the following are usually found in vegetable oils, meaning fats that are liquids at room temperature? And I think there's definitely one best answer to that. Good. So if you'll recall, the main difference between oils, you know, liquid fats, and your solid fats, like your Crisco and your butter and all this, is the fatty acids in liquid fats tend to be unsaturated. They tend to have carbon-carbon double bonds. And also, incredibly, those double bonds tend to be cis. They're never or almost never trans, which you would expect them to be, because trans double bonds are more stable than cis double bonds. But yeah, definitely the best answer is B. The other things all apply to different types of molecules. So B was the most popular answer, which makes me happy. Good, last question for today. Synthetic detergents are made by? All right, looks like that's it. Good, so all 5 of these are things, but basically what we covered was we said that you take triglycerides and you reduce them with that copper chromite or whatever it was. And you reduce, in so doing, you reduce the carboxylic acid groups to alcohols, long chain alcohols. And then we treat those with sulfuric acid, followed by a weak base to get you a long chain alcohol sulfate. So I think the best answer is C. Again, you can do any of the other 4 things, but that will not give you a synthetic detergent. So I think C is the best answer. Once again, the most popular choice, which makes me happy. And the other 8 points are just from attendance. So with that, I've run out of time anyway, so I will see you all on Wednesday. And again, as soon as I know for sure what the average of the exam is, I will let you know. I'll put that on eCampus. So have a great day. See you Wednesday. Random question is our final curved as well. It has to be. It'll be multiple choice. You have to curve multiple choice exams or it doesn't make sense. So definitely it will be curved somehow. Okay, see you all later.